So, welcome to the fifth lecture dealing with Lewis dot structure and molecular bonding. So let's go back and consider a simple compound, like one made of nitrogen and chlorine. If we combine nitrogen and chlorine, the nitrogen starts out with 5 valence electrons, the chlorine starts out with 7. So the nitrogen needs to form 3 bonds, the chlorine needs to form only 1. So the chlorine puts in 1, the nitrogen puts in 1, and we get a covalent bond. The chlorine is happy. The nitrogen needs another bond, so we have to bring up a second chlorine. It puts in 1, the nitrogen puts in 1, and we get a second covalent bond. But the nitrogen is still short, and so we have to bring up a third chlorine, which puts in 1, and the nitrogen puts in 1. And now, with 3 covalent bonds in a lone pair, the nitrogen has finally made it to its noble gas count. The 3 chlorines each have 3 lone pairs and a single bond for their 8, and so we end up with nitrogen trichloride. And it doesn't matter what quantities of nitrogen and chlorine you combine together, the only compound you get out is nitrogen trichloride, because that's the only arrangement where everybody ends up with a noble gas count. Things are a little different if we start out with boron instead of nitrogen. Boron only starts with 3 valence electrons. So the boron puts in 1, the chlorine puts in 1, we get a covalent bond. The chlorine is satisfied, the boron's still short. We bring up a second chlorine. It puts in 1, the boron puts in 1, and again we get a covalent bond and the chlorine is satisfied. The boron is still short. So we bring up a third chlorine. It puts in 1 and boron puts in 1, and we get a covalent bond and the chlorine is again satisfied. But the boron's still short, and we have a problem. The boron has run out of electrons. It would not do us any good to bring up another chlorine, because the chlorine's only going to put in its electron if the boron puts in an electron, and the boron doesn't have any anymore. And so we end up with the compound boron trichloride. And this is again an exception to our octet rule. You have to keep in mind the octet rule is a rule of thumb. That is, it works most of the time, but that there are exceptions. And it turns out boron compounds frequently are exceptions to the octet rule, simply because the boron runs out of electrons before it can form enough bonds to reach its 8. So what other considerations do we have in looking at simple compounds? If we start out with cesium and chlorine, the result is fairly simple and straightforward. Cesium starts with 1 valence electron, the chlorine starts with 7. Cesium's a metal, chlorine's a nonmetal, so the cesium simply ends up losing its electron to the chlorine. And so cesium becomes a cation, chlorine becomes an anion. We have a simple ionic compound, cesium chloride. If we don't have any cesium present, then of course the chlorine reacts with the chlorine. Each of the chlorines puts in 1 electron, and we get a covalent bond and a molecule of chlorine as a result, because the chlorines are sharing the electrons. And of course they're sharing the electrons equally. Both the chlorines have exactly the same electronegativity, and so they are both pulling on the electrons the same. This of course is completely different from what's going on in the cesium chloride, where the cesium has just outright lost the electron. The chlorine has gained the electron. There's basically no sharing. The chlorine simply gets 100% of the electron. The interesting case is when we combine chlorine with something like iodine. Iodine, of course, is also a non-metal, and so it has a high ionization energy. It's not willing to let go its electrons. So the chlorine puts in 1, the iodine puts in 1, we get a covalent bond between the iodine and the chlorine. They end up sharing the electrons. But in this case, we have something else going on. The chlorine is more electronegative than the iodine is. As a result, it pulls more strongly on those electrons that it's sharing. It is getting the better end of the deal. It's getting more than its fair share of that pair of electrons. So the chlorine is actually gaining somewhat of a negative charge since it's getting more than half the electron density. That's a lowercase Greek letter delta. It's often used as an abbreviation in science to mean a little bit of something. So the chlorine is becoming a little bit negative since it's getting more than half the share. The iodine, on the other hand, is losing. It's getting less than half the share. And so it's ending up being somewhat positive in nature. It's not letting go. It's not becoming a cation, but it is losing somewhat ground and so becoming somewhat positive. And so we have a molecule that has a negative end to it and a positive end to it. We talk about a polar molecule. A polar molecule has a dipole, that is a negative end and a positive end. You indicate a dipole in a molecule by drawing a plus sign underneath the positive end of the dipole and pointing an arrow towards the negative end of the dipole. And so the iodine's the positive end, the chlorine is the negative end of our polar molecule. And this is important because polar molecules act like small magnets. And what happens when you bring magnets together? Well, they attract and repel each other. They interact. They either want to become closer or they want to get further away. They actively are attracting and repelling each other. If you simply bring two pieces of metal together, the two pieces of metal don't care how close they are or what way they're pointing or anything else. You can do anything you want with the two pieces of metal. The two pieces of metal won't care. And that's the case we have with nonpolar molecules. They do not have any attraction or repulsion for each other. You can bring them as close or as far away as you want and it doesn't matter. But the polar molecules are like the magnets. They attract and repel each other. They interact. And so the polar molecules have a different kind of behavior than the nonpolar molecules. So if you want to anticipate what a compound is going to do, one of the things you do in fact have to decide is whether the molecules are going to be polar or not polar, because they're going to behave differently. Now, consider these four molecules: nitrogen trichloride, boron trichloride, sulfur tetrachloride, and silicon tetrachloride. All of these molecules have very polar bonds in them. And so the chlorines are pulling electrons away from everything else. So we have polar bonds. But we don't have polar molecules. Only two of those four molecules are actually polar molecules. The other two are non-polar molecules, even though they do in fact have polar bonds within them. And the question is if polar bonds don't automatically get you polar molecules, what does in fact get you polar molecules? And that brings us to the idea of shapes of molecules. And that is where we are going to go in our next lecture. Have a good day. So that concludes our series about Lewis dots and bonding. Now we're going to have to start talking about the actual shapes of molecules.